Let's continue with the second half of section 7.2. Here we are going to look at oxidation-reduction reactions. So an oxidation-reduction reaction, or commonly referred to as a redox reaction, which is the word that I'll be using from this point forward. So a redox reaction is a chemical reaction in which electrons are transferred from one reactant to another. Now, oxidation refers to the loss of electrons, so it's a species, so it's an atom or an element of some sort that loses electrons from the reactants to the products. Reduction is the gain of electrons, so it's it's an atom, a compound that gains electrons from the reactants to the products. So a helpful way to remember this is with the mnemonic device Leo says Gur, where loss of electrons is oxidation, or sometimes I just say lose electrons oxidized. And then on the other side, gain of electrons is reduction, or I'll say gain electrons reduced. So lose electrons oxidized, gain electrons reduced. Let's look at a redox example. Here we've got 2NaS plus Cl2 forms 2NaCl. So solid sodium plus chlorine gas forms solid sodium chloride. Sometimes it's helpful to focus on one reactant at a time and to split that reaction into two half reactions. So our first half reaction here is with sodium. We've got neutral sodium on the left, and on the right side you can see now that sodium has a charge of +1. So we've got 2NaS forms 2Na+. Now we do need to balance this, right? Because sodium here has lost electrons. Sodium has lost electrons. How many? It's lost 2 electrons. So we write those 2 electrons as a product. Electrons are lost to make a cation, so this is oxidation. Sodium is oxidized, so write those electrons as a product in the half reaction. Our other half reaction is with chlorine, so we've got Cl2, and then what's being formed are 2 chloride ions. So neutral Cl2, and then we're forming 2 chloride ions. So here, electrons are gained. 2 electrons are gained. So electrons are gained to make an anion, so this is reduction. Chlorine is reduced. So when you're writing your reduction half reaction, you should write the electrons as a reactant, since that species is gaining electrons. Now, even though it is helpful to think in half reactions, the oxidation and the reduction, they are not happening separately. They're really happening at the same time. It's the loss of electrons from sodium that enables chlorine to be reduced. So what we do here is we call sodium the reducing agent. It's also the gain of electrons by chlorine that allows sodium to be oxidized. So we call chlorine the oxidizing agent, right? They work in tandem with one another. You can't have one without the other. So whichever species is oxidized is also the reducing agent. Whatever is reduced is the oxidizing agent. All right, let's talk about oxidation number. So this is fairly similar to formal charges, if you recall when we talked about formal charges in chapter 4. So redox reactions are not just limited to ionic compounds in which electrons are transferred. They can also involve covalent compounds in which electrons are shared. So for covalent compounds, we use a concept called oxidation number. Here, this is a charge an element in a compound would possess if that compound was ionic. Okay, so there are some rules for oxidation numbers, and now these rules, again, will be provided on the reference sheet. You don't need to memorize them, but you do need to know how to use them. So the oxidation number of an atom in an elemental substance, so the way it is found in nature when it's just by itself, is 0. The oxidation number of a monatomic ion is just equal to that ion's charge, so easy enough so far. Now, it should be mentioned that the sum of oxidation numbers for all atoms in a molecule or polyatomic ion must equal the charge on that molecule or ion. And you want to follow the order in this list from top to bottom. So at the top, the items towards the top take priority. So fluorine getting assigned -1 takes top priority. Then the group 1A or 2A metals. So group 1A metals are +1, group 2A metals are +2. Then hydrogen, then oxygen, then group 7A other than fluorine, so chlorine, bromine, iodine, and then anything else is assigned last and depends on what it is bonding with. Okay, so let's look at a couple examples. Let's start by looking at potassium permanganate, KMnO4. So we want to start with the oxidation numbers we know. So first thing we want to assign is potassium. We know potassium is +1, and there's one of them, so the total contribution to the charge is +1. Next, we can go to oxygen. We know that oxygen has an oxidation number of -2. There are 4 of them, so the total contribution to the charge is -8. So this molecule is neutral. So we've got +1 coming from that single potassium atom. We've got -8 coming from those 4 oxygen atoms. So this means that manganese here has to be +7, has to be contributing +7 to make this compound neutral, which means manganese's oxidation number is +7. I do also want to highlight here that if I asked you a question like this in the exam, where I asked you to give me the oxidation numbers of these 3 compounds, these would be the answers: +1, +7, and -2. If you told me the oxidation number of oxygen is -8, that's wrong. Oxygen's oxidation number is -2. It's just its total contribution to the charge is -8 because there are 4 of them. Let's look at another example, H2SO4. So here, hydrogen gets first priority. Its number is +1, so the total contribution is +2. Next, oxygen, again, its number is -2. Total charge contribution is -8. So sulfuric acid here, H2SO4, is neutral. So we've got +2, we've got -8. So this means sulfur must be +6 to make this compound neutral. Okay, I'm going to start going through these fairly quickly since I've got a lot of examples to show you. So ClO3, the chloride ion, oxygen gets first priority. Oxygen is -2. There are 3 of them, so the total contribution of the charge is -6. Now pay attention here. These 2 boxes, the total charge contributions, they have to sum to the overall charge of the molecule, or in this case, the polyatomic ion. So whatever this number is plus this number must sum to be -1. So that means chlorine's oxidation number here is +5. Let's look at sulfur dioxide, SO2. Oxygen is -2. Total charge contribution, -4. So sulfur has got to be +4 here. So oxygen's oxidation number is -2, sulfur's is +4. Okay, here's a tricky example. This one often trips people up. Sodium hydride, NaH. So if you go and you look at those rules, so a lot of people here, they think, oh, hydrogen's got to be +1, so then I guess sodium is -1. But if you look at the oxidation number rules, the group 1A metals actually get a higher priority than hydrogen. So sodium's charge here is +1, which actually means that hydrogen is -1 here. So sodium's oxidation number is +1, hydrogen is -1, since group 1A metals get a higher priority on the oxidation number rule list than hydrogen does. All right, let's look at carbonate, CO3 2-. Again, oxygen is -2. We've got 3 of them, so this is -6. So whatever this number is, this number plus this number must sum to -2, since that's the charge on the ion. So here, carbon is +4. Okay, I'm going to jump through this example. Oxygen -2. There are 5 of them, -10. So total charge contribution is +10, which makes nitrogen +5. All right, let's get to this knowledge check question. What is the oxidation state for sulfur in HSO3-? So give this one a try. Okay, correct answer here is +4. So oxygen is -2. There are 3 of them, so that's a total charge of -6. Hydrogen is +1, so we've got +1 and -6. And we've got an overall charge of -1, so sulfur here must be +4. Now let's look at how we can use these oxidation numbers. We can use them in equations to track whether there's an increase or decrease, and we can also use this to determine whether an element is oxidized or reduced. So let's look at this example. We're going to start with H2 and F2, so they are both in their elemental natural state, so they both have oxidation numbers of 0. Now we'll move to this compound. Fluorine gets that -1 first, which means hydrogen's got to be +1. So now if we look, hydrogen's initial oxidation number was 0. Its final oxidation number was +1. So its oxidation number increased, or you can also think of this like its oxidation number got more positive. Therefore, hydrogen lost electrons and hydrogen was oxidized in this reaction. This also makes it the reducing agent. Fluorine's oxidation number decreased. It went from 0 to -1, or if it helps, you can think of it like its oxidation number got more negative, which means fluorine gained electrons and was therefore reduced. We could also say that fluorine is the oxidizing agent. Let's look at a few more examples. This is a single displacement or single replacement reaction. So here we've got elemental zinc. It's by itself. It doesn't have a charge, so its oxidation number is 0. We've got the ionic compound, copper chloride. So chlorine is -1. There are 2 of them. Total charge contribution is -2, which means copper is +2. And it's the same thing on the other side. Chlorine is -1, zinc is +2, and then copper now is in its elemental state, it's 0. So chlorine's oxidation number doesn't change, so nothing happened to chlorine. Zinc went from being 0 to being +2. Its oxidation number increased, so therefore zinc is oxidized, whereas copper, its oxidation number decreased. It went from +2 to 0. It gained electrons, so copper is reduced. And then again, we could also say that zinc is the reducing agent, and copper is the oxidizing agent. All right, let's have you try a knowledge check question. Which of the following is the reducing agent, and what is reduced in the following reaction? This is a single replacement reaction. All right, and the correct answer here is A. Zinc is the reducing agent and copper is reduced. So zinc was oxidized, it went from 0 to +2, so therefore it's the reducing agent, whereas copper is reduced, it went from being +2 to 0. Let's look at a combination redox reaction. I do also want to mention you're going to want to know the names of these types of reactions. Now what's helpful is the names are very descriptive. So a combination reaction, they have 2 or more reactants combining to make one product. So for example, nitrogen gas plus hydrogen gas, we've got 2 reactants, we've got one product. This is a combination reaction. They can involve oxidation and reduction. So here, nitrogen gas and oxygen gas, their oxidation numbers are 0 since they're in their elemental state. Over here, we assign +1 to hydrogen first. There are 3 of them. Total charge contribution is +3. So then nitrogen must therefore be -3. I do also want to mention coefficients don't affect these oxidation numbers. So if we take a look at this, oxygen went from 0 to +1. Its oxidation number increased, or it got more positive, therefore it lost electrons, so hydrogen was oxidized. Nitrogen went from 0 to -3. Its oxidation number decreased, or it got more negative, meaning nitrogen gained electrons and it was therefore reduced. Okay, this is an example of a decomposition reaction. So again, this name is pretty descriptive. A decomposition reaction involves one or more reactant, involves one reactant. So it's the reverse of a combination reaction. We've got one reactant, and it decomposes to make 2 or more products. And they are typically redox reactions. So here, we're showing sodium hydride decomposing to form sodium and hydrogen. So if we start with our reactant, again, sodium gets first priority. It gets that +1, which makes hydrogen -1. And then sodium and hydrogen are both in their elemental states. Their oxidation numbers are 0. So if we take a look at this, hydrogen now is being oxidized. It's going from -1 to 0. Its oxidation number is increasing, or it's getting more positive. So hydrogen is oxidized and is the reducing agent. Here, sodium is going from +1 to 0. Sodium is being reduced since its oxidation number decreased, or it got more negative, it gained electrons. So sodium is reduced, and it is also the oxidizing agent. Okay, finally, let's look at combustion reactions. Combustion is also a redox process. So we've talked about these a lot already. Combustion reactions are all the same. It's some sort of hydrocarbon, so usually it just has carbon and hydrogen, but there could also be oxygen in this compound. But the other 3 compounds are always the same. Oxygen gas is your other reactant, and then your products are always carbon dioxide and water. So that's a telltale sign you've got a combustion reaction. It's some sort of hydrocarbon plus oxygen gas, and the products are carbon dioxide and water. And then obviously a lot of heat is given off. So let's start with methane over here, CH4. Hydrogen gets +1. There are 4 of them, so total charge contribution of +4, which means carbon is -4. Oxygen is 0. It's in its elemental state. Here with carbon dioxide, again, oxygen is -2. So now carbon is +4. And over with water, hydrogen gets first priority. It's +1. There are 2 of them. So this means oxygen is -2. So if we take a look at this, Hydrogen is the same on both sides, right? Hydrogen's oxidation number is +1 on both sides. But what did change is carbon and oxygen. Carbon went from -4 to +4, so carbon is oxidized. And oxygen went from 0 to -2, so oxygen is reduced. Okay, now let's talk about going from half reactions to the full reaction. So redox reactions, they can sometimes be the sum of an oxidation half reaction and a reduction half reaction, especially if we are looking at a single displacement reactions or a double replacement reactions. Typically when we're looking at ionic reactions here, we can write these oxidation and reduction reactions or these redox reactions as half reactions. So for example, this is a redox reaction and we can split this into half reactions. We've got our oxidation half reaction where zinc has been oxidized, and we've got our reduction half reaction where copper has been reduced. So we can write those like this, and then they can be recombined to cross out the electrons. And so we just get what we started with. So here, okay, right now this doesn't seem that useful, but let's look at an example where it is useful. Let's look at an example of a type of problem I may give you on the exam. Suppose I give you this reaction right here. I give you this redox reaction where we've got solid chromium plus nickel forms chromium ions and solid nickel. So these redox reactions, not only must they both have mass balance, right? The equations must be balanced, just like we've seen earlier in this chapter, but they must also have charge balance. So if we take a look at this, the masses are balanced, right? We've got one chromium on each side, one nickel on each side, but the charges are not balanced. We've got a +2 on the left, and chromium is providing a +3 on the right. The charges aren't balanced. So what we want to do here to balance this is we want to split this reaction into its half reactions. So we're going to get our oxidation half reaction. So chromium is being oxidized here. It's going from 0 to +3. So this is our oxidation half reaction. Chromium forms Cr3+, and it gives off 3 electrons. We've also got our reduction half reaction. Nickel is being reduced here. It's gaining 2 electrons. Now you want to take a look at this, and you want to make sure the electrons are balanced. Our oxidation half reaction has 3 electrons being lost, whereas our reduction half reaction has 2 electrons being gained. We need to balance this. So what we need to do here is we need to multiply by an integer. So if the electrons are not the same, multiply each half reaction by the number of electrons from the other half reaction. So I'm going to multiply that first reaction by 2, and I'm going to multiply that second reaction by 3. And so I get 2Crs forms 2Cr3 plus 6 electrons. And with my reduction half reaction, I get 3 Ni2 plus 6 electrons forms 3 NiS. Now I can combine these because the electrons successfully cancel out. So just like spectator ions, the electrons have got to cancel out here, which gives this as my final answer. 3 Ni2 plus 2Crs forms 3 NiS plus 2 Cr3+. Now you see we've got 2 chromium atoms on both sides, 3 nickel atoms on both sides, so the mass is balanced, but now the charge is balanced as well. I've got +6 on the left and +6 on the right. So let's have you try this knowledge check question. Balance the following equation in neutral solution using the half reaction method. So split this into the half reactions, make sure the mass is balanced, then make sure the charge is balanced, and then recombine to get your final reaction. Okay, correct answer here is D. 2Cr3 plus 6Cl minus forms 3Cl2 and 2Cr. So first I'm going to start with my oxidation half reaction. So my oxidation half reaction here is Cl minus forms Cl2. So first thing I need to do is balance the masses. So I need to place a 2 right there to balance the masses. Now I need to balance the charges, so I need 2 electrons on the right side there. Next, I'm going to go to the reduction half reactions. This would be Cr3 plus 3 electrons forms Cr. So now my masses are balanced and my charges are balanced. Last thing I want to do is I need to multiply both of these by an integer. So I multiply that top reaction by 3, multiply that bottom reaction by 2, and then when you recombine, the 6 electrons cancel out, which gives me 2Cr3 plus 6Cl minus forms 3Cl2 plus 2Cr. Okay, so that concludes this section. Here are a few more practice problems for you to try. So pause the video, take a few minutes to try these practice problems. Once you have done so, here are the answers to those problems. That concludes section 7.2. I'll see you in the next video for section 7.3, reaction stoichiometry.